Here. You gotta do, you have to take it out. Got no one in.
Okay, so here we go. We started on cells last time, and I realized I did, we did great. Talking about the things we did, we came at it very organically because we were kind of coming out of that study guide and things like that. And we really started with the membrane, right? The outer membrane, the phospholipid bilayer. It's also got proteins, and it's got carbohydrates and stuff that are embedded in it or attached on it. The inside of it is hydrophobic, and the outside is hydrophilic. So the outside likes to be near water, the inside does not. That's why it forms the bilayer. The fact that it's made out of these phospholipids with these fatty acids means it's very oily, it's very movable, right? It's really important. If it were rigid, it would be very hard to get stuff in and out of it. Now, one of the things we kind of just said about it very generically, like it's, probably the doctor would probably cringe at me saying this, but a cell membrane is there to keep inside things in and outside things out, and to regulate the passage of stuff. If you got a bunch of toxic stuff out here, you want to keep it out here, right? If I've got a bunch of toxic stuff in here, I want to get it out of here. If I've got a bunch of sugars and stuff, I probably want to get it into the cell. And once it's in the cell, I want to keep it in the cell. I don't want stuff just free-flowing everywhere. That's happening if we're just losing stuff and things can move wherever they want, then we are not going to be able to do probably the number one task of all of life. You ready? You just missed something very important. The number one task of a cell, the number one task of life is to do this. Maintain homeostasis. These are cute little pens. Can y'all read that? Okay. Maintain homeostasis. We talked about this last class a little bit, right? It's the idea of maintaining a steady state, a constant set of conditions. This really, really matters a lot. You need a certain set of conditions inside of a cell. You need a certain set of conditions inside of your body. And if conditions outside would try to change those, you've got to be able to regulate things, right? I believe it actually worked out really well. Man, you got cold, and we started talking about maintaining homeostasis with temperature. And so you adapted, you put on a sweatshirt or something like that to keep yourself warm, right? At the cellular level, they do things to regulate this. So probably the number one organelle for maintaining homeostasis, like if you don't have this, give up the game, you don't have a cell, is the cell membrane with that phospholipid bilayer, right? And so we said, hey, I've got stuff out here, and I've got stuff in here, and I need to be able to regulate them. So let's think about this. If you are a fish, or you're some little small organism, and you live in the ocean, what's life like outside of your cells? What do you know about the ocean? Lots of two things.
Water.
Water, and what's in that water? Dissolved in that water. Salt. So here's a bunch of salt. Like you live in water, right? But here's all this salt, okay? Just all over the place. And salt's fine, but you can't have all this salt inside of your cells. That will cause you problems. So you got a lot of salt outside, you don't want a lot of salt inside. So some things happen when you have an environment like this, right? Everything in creation, this is the second law of thermodynamics, and the second law of physics. Everything is trying to move from a high to a low concentration. I have a high concentration of salt out here. What does the salt want to do? Wants to move in. Salt wants to move in. I have, compared to the outside, a high concentration of water. Does water want to move in or water want to move out? Water wants to move out. If salt moves in and water moves out, do you know what happens to this cell?
It dies.
It shrivels and then dies. We'll kind of start to, my nice plump cell here will kind of become that. You can actually do that. You can put a little cell in salt water and just watch what happens. It's going to shrivel up, and then it's not going to be able to do the rest of what it needs to maintain homeostasis. So the membrane is very important for keeping outside things out and keeping inside things in. Regulating the passage of things inside and out. Something like salt, though, salt flows pretty freely. Water flows pretty freely. The membrane just sitting there isn't able to just go like, no, you shall not pass. Instead, it's got to actively put stuff inside or outside. Either it's got to actively get a bunch more water in to compensate, or it's actively got to pump sodium out and able to maintain homeostasis. Now, I need to throw a couple terms at you, okay? Related to kind of pausing. So we're going to come back to the rest of the organelles, but we're really going to focus on these membranes, okay? So one of the things that it does, or one of the things we want to consider, is an idea of hyper and hypotonic. Okay? So, this is going to be hypertonic. This is going to be hypotonic. Just relatively speaking. So what happens in these situations is these terms reference the solutions on either side of a semi-permeable membrane, which is what this is, right? It's semi-permeable. Stuff can flow in or out of it. So if I put a cell in this environment and I do nothing, those solutes are going to move in, and that water is going to move out until they are in equal concentration. And then it will be what's called isotonic, okay? Let me give you another drawing of this. Okay, so we're going to have just a cell or some kind of semi-permeable membrane here, okay? So on one side of it, I'm going to have a lot of what we call solutes. Do you know that term? You need to know it. So solutes are dissolved particles. Okay? Solutes are dissolved particles. In my hypertonic environment over here, I've got more solutes. Over here in my hypotonic environment, I have fewer solutes. If they can, then those solutes will move across my membrane until the two sides are in equal concentration. If water can, it will move out across to the hypertonic until the two sides are in equal concentration. So move from, I'll do a similar drawing over here to show you just kind of what this would like to look like. Okay, so Here's my membrane again. Now, basically we're answering a question, what if this is permeable to both, okay? Permeable means it can pass through, right? So if this membrane is permeable to the solutes and to the water, and I left this sitting for an hour, what I would expect to see when I came back was what? What would you expect to see?
Same concentration in this one?
Tell me. What should I draw here? What should it look like? Where should my purple dots be? On one side or on both sides? Both sides. Yeah, if it's permeable to both, then I will expect to see an equal concentration of both on both sides, right? There will be fewer over here, and there will be a whole lot more over here than there were originally, right? And at this state, we are what's called isotonic. Now, one thing about isotonic is, it's not like they stop moving. These things, they go, hey, let's pack our bags and move on to the hypotonic side of the tracks. They're just flowing all the time. This is how they move, but by random diffusion, they move, they spread, they pass. These are still moving back and forth, but on average, for every one that moves here, one moves here. That makes sense? Hopefully? Okay. You make me feel better about myself when you say yes. That makes sense. You did a great job. All right. So this is hyper and hypotonic, and this is isotonic. Now, let's do this. I should not have erased that. Same concept. Okay? Actually, not same. Here, I'm going to draw a cell this time, okay? So if I have a cell, and there are lots of solutes out here and none inside the cell, and the cell is impermeable to these solutes. The solutes cannot get across. What is this going to look like after an hour?
Empty. Inside.
It's already empty inside.
Still gonna look empty.
It's going to
Stay the same.
shrivel. It's going to shrivel. Well, why did it go from this to this?
Salt.
Salt couldn't get inside, or the solute could not get inside, so what happened instead? The water moved out. Yeah. Until essentially they had the same concentration. This one has like nothing left inside. Let's do another one. Same situation, my cell is not permeable to these solutes. All the solutes are in my cell. None are outside. My solutes cannot move outside of my cell. What will happen instead? Water will move into my cell. What's going to happen to my cell?
It's gonna explode.
It's ultimately going to break. Yeah, it's going to lysis. Split into pieces, and now, I'll just have stuff floating everywhere, right? It's called lysis.
So, cell membranes can only be impermeable to solutes, not water.
They're always permeable to water.
Okay.
Always. Some solutes they're really permeable to, like salt. Salt's, it's tiny. But other things like sugar, it's not permeable to. Something like sugar, if it wants to get sugar inside the cell, it has to actively be able to get it inside the cell. Right? It has to have a mechanism of doing that. Either it has to pass it through like a protein-gated channel, or it's got to engulf it. Remember last time we talked about phagocytosis and pinocytosis? Let me give you a quick rundown of that, okay? Do it here. So we talked about this last time. We looked at a video of it. If you need to go look at that video because you forgot it or because you weren't here, go check it out. It's on the Moodle, okay? But there are how am I going to title this? I'm just going to say cytosis, okay? There are two types. There's endocytosis, and what's the other one?
Exocytosis?
Exocytosis. Which one moves stuff in?
Endocytosis.
Endo. Which one moves it out?
Exocytosis.
Good. Okay, so I have endocytosis and I have exocytosis. Under endocytosis, I'm looking at two types. One is phagocytosis, and the other one is penocytosis. What does penocytosis mean?
Cellular drinking.
Cellular drinking, and phagocytosis is cellular eating, right? Okay, that's a good chart to be able to remember, by the way, just to help organize our thoughts. So when we talk about endocytosis and exocytosis, we're talking about, like, especially if it's endocytosis. So I've got something out here that I want to bring inside of my cell. My cell membrane is literally going to have to, like, begin to engulf this thing, right? And then it'll move even more like this, and then ultimately it will completely engulf it and fuse it inside of what's called a vesicle. And then it'll take that and modify it. This is phagocytosis, right? If it was water that I was doing this with, it would be penocytosis. And of course the opposite is true. If I had something in here and I wanted to get rid of it, and it's big, right? Then I can put it in a vesicle, and then I can bring my vesicle kind of over to my membrane, right? And then ultimately I can kind of fuse the vesicle with the membrane. And then I can basically push it out of the membrane. Okay?
So what's the point of even having it in vesicles? Like, what's the point of even having it if it's not inside the cell?
The vesicle is always going to be inside the cell.
Yeah, but it's like outside the membrane, right? Because it's like on the outside of the membrane, the part that likes water, right?
It's a phospholipid bilayer, right?
That's what the phospholipid bilayer, right? Because it's like in a bubble, right?
Yes.
So what is it doing to the cell? How does it help the cell?
Well, if it's sugar, right, then a whole bunch of sugars, then I engulf this, or I engulf this thing, right? And now it's inside here. It doesn't stay in there. Vesicles don't just remain as vesicles forever. They fuse with other. We're just barely getting started with the life of a cell. They're going to fuse with other organelles. Metabolism's going to happen. Catabolism, anabolism, all that kind of stuff.
So it just starts like that.
This is right now. We're just looking at how do I get it in and out. That's it. But there's going to be a whole host of processing and packaging that happens inside of a cell. That's good. Okay. So this would be a good time to say this. That I probably should have started off with last time, but we started from a unique point because of where we were in our study guide. So let's look at types of cells, okay? Some things are going to be true of all cells, and some things are only going to be true of some cells. So I'm going to give you another flow chart, because I like flow charts. They're fun. Markers everywhere. There we go. That's the one I want. Let's look at cells, okay? We're going to go prokaryotic. And we're going to go eukaryotic. So there are two, right away when we talk cells, we can divide all cells into just two classes, either prokaryotes or eukaryotes. So prokaryotes, the word pro means before, okay? That's significant. So these have no nucleus. These are things like bacteria and archaebacteria. Later on, we'll further break those down based on other cell parts that they do and don't have. But that's the basic of it. If you were to see a cell and it has no nucleus, there's a pretty good chance that it's a prokaryotic cell. There's one more thing. In addition to no nucleus, have no membrane-bound organelles. In other words, they don't have any organelles, and that term organelle means like mini organ. Think about your heart, it does one task, right? Your lungs do another task, your brain does another task, your liver does another task. It's the same way in organelle. They're collections. It's kind of like an organ. A cell is kind of like our organ system, our organism. It's a collection of little organelles that carry out specific functions that cooperate together to make life happen. So you have lots of organelles that are what we call membrane bound. They're associated with membranes, they're attached with membranes, they're wrapped up in membranes. Having a phospholipid bilayer is an integral part of their function. That's not the case with prokaryotes. Okay, so the key things here that distinguish them is no nucleus and no membrane-bound organelles. Your types are bacteria and archaebacteria. You must know that. Okay, I guarantee you that you will have questions about that on a test. All right. Then we go over to the eukaryotic cells. So if these had no nucleus, then these have a nucleus. Okay. We'll get to that in a second. I want to talk about our types. There are 3 types here. Okay. Plants, animals, and fungi. We'll learn more about the distinctions of these pretty quickly in this chapter. But key things here are have a nucleus, right, and have membrane-bound organelles. Train's a little loud, isn't it? Does it go at night? Keep you up? Prokaryotic and eukaryotic cells. These are the 2 major groups. Plants, animals, fungi. I'm going to draw some cells. You tell me everything you can about that cell, okay? Okay. Tell me what you see. What is this? What am I pointing at? Not the whole cell, but what part of the cell am I pointing at? Cell membrane. Good. What's that? Nucleus. What's that? What are these?
Nuclei.
Nuclei. Good job on the plural on that. But they're nucleuses. So, what kind of a cell is this? Prokaryotic or eukaryotic? Eukaryotic in this one? Eukaryotic in this one? Eukaryotic. What is this one? Prokaryotic. Which of these is going to be a bacteria? I'll label these. We're going to go A, B,
A.
C, or D. Which one's a bacteria?
A.
A. Which one of these is a plant?
B,
How do you know?
the cell wall.
Cell wall. Can't be an animal. If you had a cell wall, this would be you. This would be you playing soccer. This would be you listening to Justin Bieber. This would be you doing your homework. This would be you. You can't move. I got her with Justin Bieber, huh? I couldn't name a Justin Bieber song if my life depended on it. But I'm old. So, these have a cell wall. We're going to talk about that in a second. What about this one? That's weird. It looks like it's got a cell wall, but it's a funky cell wall. And it doesn't have one nucleus, it has two, and it does not have this. So this can't be you, right? Because this would be you. What is this? Fungi. Has a cell wall. And a whole lot of nuclei. Very strange. So this must be my animal, right? No cell wall. Free to move and do tricks and play soccer and get concussions. All those kinds of things.
Yeah.
Scott jokes, folks. So you actually just learned a lot, right? Plants, some defining characteristics of plants are cell walls and chloroplasts. Some defining characteristics of fungi, cell walls, and many are polynucleate. That's so weird. Some defining characteristics of animal cells, no cell walls, and high mobility or motility. Smart, just taking pictures. So let's look at this for a minute. This matters. Let's think about our B here, okay? If I put B in an environment where there are not many molecules around it, but there are tons in it, right? So is the cell hyper or hypotonic?
Hypertonic.
Hypertonic. So, and I can't get these out, then what does water want to do? Water wants to rush in until the cell explodes. But I've got this thing called a cell wall. So my cell, after a little while, will look like this. It's going to have a lot of pressure up against that cell wall. Or it could look like this. What if I put it in an environment where there was a lot more solute outside? Then what's it going to look like?
It's gonna wanna show up.
It's going to want to show up. Right, it's going to go like this.
So the cell wall is just making it hold its shape on the outside? Like it's just there as a structure?
Yeah, the cell wall is a fairly rigid, not 100% rigid, but fairly rigid structure. It provides what's keeping me up right now. Why am I not just a pile of ooze on the floor?
Bones.
Bones. Plants don't have bones, right? What keeps a tree from being a pile of ooze on the floor? Cell walls. Cell walls keep it from just, okay. Do you know actually in plants, certain types of plants anyways, they will grow certain cells and then those cells die. But their whole function was ultimately for the mature plant to form these non-living structures just to give it shape and strength. It's really, really cool. And it can transport water through them and stuff like that. It's called xylem. And then do you know that like on the inside of the tree it's dead? That's not those aren't living cells. The living part of a tree is on the outside. The bark and the layers of cells just inside of that. That's called phloem. You want to kill a tree? You want to go murder trees? You don't have to cut the whole tree. Get yourself a piece of wire and wrap it around the tree and just go back and forth like this. And just dig into the bark far enough that you separate the phloem layers. And now the sugars can't flow down to the roots and the root can't control what's happening to the water and stuff can't flow and the tree will just die. It'll just die. So there you go. But yes, this provides a shape, right? And so when they get desiccated, that's what this is, when they shrivel, then that's a problem, right? These cells may not recover. But when they get too much, or another term is flaccid, but when they have a lot of what's called turgor pressure, you don't have to know these terms yet, but I'm throwing them out there because they're the right terms, and you will learn them soon enough, certainly by next semester. When it gets enough turgor pressure, it extends out against this. This is important. These cells can open or structures on plants can open and close based on turgor pressure. They can regulate things. And so the cell wall keeps this from exploding. You've got living tissues in the roots, in the water, and so you get a big rain, right? And so there's just water flowing all around it and flowing into it. You don't want those cells exploding and the tree dying, right? So you better have a cell wall to keep it from exploding. Vegetables. Y'all ever get like some lettuce or something like that and it just like it's all like leaning over limp? Yeah? Where you get a flower and the flower's doesn't look like it's doing so good. What do you do with that flower that's not looking like it's doing so good? You put it in water. And the water flows up and those cells that were looking a little more like this start to look like this. And those petals that were all wilty begin to. And this works with vegetables and stuff too. If you've got like lettuce and it's looking terrible, put it in a little bit of water and it will stiffen right back up. It's all this. That's all it is. It's this. You're able to see it at a macro level. Okay? So, I need to throw a couple more terms at you. All right? Which one do you want me to erase? The pictures? Okay. So, diffusion. We talked about that, right? What is diffusion? No? Okay, diffusion is the random movement of particles from areas of high to areas of low concentration. I don't do this very often. This morning, I don't know, I put on this shirt and obviously it hadn't been washed since the last time, and I think the last time I wore it, I probably had on some cologne, so I smelled the cologne. I was like, I'll put on cologne this morning. So I walk over and I've got this bottle and I go, and I walk into it, right? Do you smell the cologne? No. It's pretty diffused at this point. But if you were in my bedroom this morning and you were my wife, you would have smelled it. Like it would have been very concentrated, right? If I had a bottle of perfume or cologne or something right now and I sprayed it, at about 2 seconds, do any of y'all smell it? No. But after 10 seconds, can he smell it? And after 30 seconds, can you smell it? And after an hour, if somebody walked in the room, maybe they smell it. Maybe. Because it starts off super concentrated. It's there in that bottle, and when I first spray it, it's just there right in front, right? And if you were right there, you'd be like, wow, that's a lot of cologne. But it will diffuse, it will spread out over time. It will move from an area, randomly move from an area of high to an area of low concentration. It will do this until it has an equal concentration everywhere, until there's even distribution of particles. If I had 2 glasses of water and one of them had some red dye in it and one of them did not, and I pour a little bit of the one with the red dye into the other cup, what's going to happen? Over time, what's going to happen? The red dye will diffuse everywhere evenly, right? Not at first. It's going to take a little bit. It's going to randomly move from high to low concentration. This is the concept of diffusion. This is a huge, huge concept. Things moving from high to low concentration. This is one of the principles that governs the universe. We see this in physics everywhere. Everything goes from high to low concentration. Everything. I think I told you this on the first day of class, right? Heat goes from high to low concentration. I got hot tea in here, right? Well, what's happening is that the heat will diffuse. It will move from inside to outside. If you were to touch this, even though it's very well insulated, if you touch the top, it's still warm, right? Because the heat's in here, it goes from high to low concentration. If I came back to this tomorrow, will this still be hot? No, where'd the heat go? It diffused, right? It moved from high to low concentration. It's the same thing with the cologne, it's the same thing with everything. This is how the universe works, right? Okay. Now we need to talk about a very special case of diffusion. This is osmosis. You must know this word. We'll be here forever, okay? So osmosis is the special case of water diffusing across a selectively permeable membrane. Special case of water diffusing across a selectively permeable membrane. It's huge at the cellular level, where your cells are swaddled in membrane. So why did that, when we drew that plant cell and it got big and it pushed up against the cell wall, that was the case of?
Sorry, say that again?
When we drew a plant cell membrane, and at first I had this little cell, right? or here's the cell wall, here's the cell, but then, oh, water flowed in, right? And so it got really, really big and had a lot of turgor pressure. That's called osmosis. Water diffused into the cell. The opposite is also true. If I had this cell here, and I had a bunch of solutes out here, and the water flowed out and the cell shriveled, that's called osmosis. A special case of water diffusing across a selectively permeable membrane. This is happening all the time in your cells. Stuff's flowing in, stuff's flowing out. Stuff's flowing in, stuff's flowing out. And if you don't have the way of controlling it, you will die. You must maintain homeostasis. You must be able to control osmosis. You must be able to control diffusion. You must be able to control endocytosis and exocytosis. Get the things you want in, and the things you want out, out. If you can't do that, you will die. It's that simple. Osmosis and diffusion both happen because of this word. You ready? Say entropy. Entropy. Entropy is the tendency of all things in the universe to go from high to low concentration. It is the second law of thermodynamics. And you, my friends, are an anti-entropy machine. If you can't fight entropy, you die. If you can't maintain homeostasis, thermoregulation, osmoregulation, you die. And you should not be able to do this. But you have been fearfully and wonderfully made. And God has given you all of the organelles and everything else that should not exist. All the laws of physics say that this is impossible. And yet here you are killing it. You should not exist. Life should not be possible. Well, all that is about membranes. Of course, we looked at cells, prokaryote. What do these two have in common? For sure they have in common. One thing you know. Cell. How do you know it's a cell? What does it have to be a cell?
Membrane.
Must have a cell membrane. That's it. They must have that. What do all of these have in common? One thing you know. If I looked at that cell, it had better be there. They must have a nucleus. What's one thing that these two must have in common?
Cell walls.
Cell walls. Good. Good, good, good. That's great. Okay. Well, felt like a lot. Want to watch a video? Let's watch a video. I like videos. We'll watch a video and we'll talk about it.